Greetings to you all. My name is Joshua, and allow me to talk about determination of percentage of sodium oxalate in a mixture of sodium oxalate and oxalic acid. This question can be asked in the other way around, determination of oxalic acid in a mixture of oxalic acid and sodium oxalate. So it doesn't matter how it is set, but what you should know is that when it involves anything to do with oxalate ions, then we have to get a strong oxidizing agent like potassium manganate 7. We react it there with the oxalate ions, then we can easily determine them using the standard solution of potassium manganate 7. Okay. So you're provided with a question of that nature, for example, 8.7 grams of a mixture of sodium oxalate and anhydrous oxalic acid was dissolved in a liter of water. Then 25 of this partial solution required 15 of 0.1 molar sodium hydroxide for complete neutralization using phenolphthalein indicator. The resultant solution was then acidified with the sulfuric acid and heated to around 70 degrees Celsius, and it required 33.4 centimeters cubed of 0.02 molar potassium manganate 7 solution. Determine the percentage composition of sodium oxalate in the mixture. We start. To interpret this question, the sodium hydroxide that we are involving in here is a base, so it will react with an acid in the mixture. So it reacts with the anhydrous oxalic acid. Now, in that case, remember we shall be forming sodium oxalate and water. So the sodium oxalate ions are increasing. But we shall not be interested in what is formed. We shall be interested in what was there originally. So we've not been given the real mass of the sodium oxalate, because what we are having, this particular 8.7 is for the whole of this mixture. So we can get the one for the oxalic acid. So we get the sodium oxalate in the oxalic acid, and then we go on and find out total oxalate ions with the potassium manganate 7, because you can see it's what is going to be reacting. And now for it, it's not going to choose. It will react with all the oxalate ions which will be available. So out of all those oxalate ions involved, I will remove the oxalate ions of the anhydrous oxalic acid. Then I remain with the oxalate ions for the sodium oxalate that was originally there. Then I can move on and get its percentage as required. We start. Equation. We know very well that oxalic acid is H2C2O4, just like that, and is a solution. This one reacts with the sodium hydroxide solution, and because it is acid base, we shall be able to form a salt, which is sodium oxalate, and water. That is how we write sodium oxalate, just like that, alongside the water, which is just like that. Now, when you go on to balance this kind of an equation, you require a 2 on sodium hydroxide, and you also require a 2 on water so that you balance the hydrogens. So we have that kind of an equation. Remember, we've been given this one, the sodium hydroxide. So we have it. So we can use this sodium hydroxide given to get the oxalic acid that we are interested in. After getting the oxalic acid, then it is so easy for us. We shall have already got even the number of moles of the sodium oxalate which can be produced by the oxalic acid present in that kind of a mixture. But remember, because we shall have formed the oxalic acid, this oxalic acid here, it's going to be now along with the one which we had originally, and both of them will be reacting with the potassium manganate 7. So we expect that in the end, the concentration that potassium manganate 7 reacts with is for, first of all, the original sodium oxalate and these sodium oxalate ions that we are getting from the oxalic acid. But we start with the oxalic acid. Let's start. We've been given that sodium hydroxide, which was involved, is 0.1 molar, and it was 15 centimeters cube that was involved. So we get number of moles, just get moles of the sodium hydroxide. This one should not always worry you. Just do like that and you get the answer as your 15. We have 15, which is the volume, times 0.1, and we divide it by 1000, because if I have molar, then it means it is for the volume of 1000. And I will be able to get the answer here, and the answer I'll be getting is going to be in moles. So it's going to be 1.5 times 10 to the power negative, I think, power negative 3. Let me try to use the calculator here and I see what we actually get there. Times 10 to the power negative 3 moles. That's number 1. Then you compare and you say that actually it is 2 moles of sodium hydroxide, we know very well, react with, of course, 1 mole of oxalic what? Acid, C2O of 4. So it means that if that is the case, then the oxalic acid required in this particular case is going to be a half. So moles of oxalic acid, the H2, C2O4 equal to a half. So it's 1 out of 2 times the 1.5 times 10 power negative 3. And this one gives us an answer of 7.5 times 10, of course, to the power negative 4 moles. So we've got the number of moles of oxalic acid. Now, these moles we've got are the same as the moles of the sodium oxalate. Got from oxalic acid, like I've told you, you can see it is 1 mole for 1 mole. So I don't need to convert anything. I'll just move with that, but I have to convert everything maybe to 1000 centimeters cubed so that I will be able to get everything accordingly. We move on. So, from there, we look at determining. So we've known, remember we have the volume which was used, 25 centimeters cubed of the solution has 7.5 times 10 to the power negative 4 moles of oxalic acid, moles of oxalic acid, C2O4. If that is the case, how about if I'm having the 1000 centimeters cubed? So I want to get it in a liter, because the solution we are dealing with is for a liter, so I don't need to. I have to keep on keeping it to the liter until when I finish everything. Of this same solution, let me just quickly do it. has the 7.5 times 10 equals to power negative 4 out of 25. Then you multiply this one by 1000 times 1000. And the answer you get is going to be the molarity. And I think this one, if I'm to use a calculator here, is going to be giving us 0.03. 0.03 molar. So I have got the molarity of the oxalic acid. Remember, this is the same as the molarity of sodium oxalate in this particular case. So we can say that 1 mole of oxalic acid C2O4 produces 1 mole of the sodium oxalate. Sodium what? Oxalate. So we've known now in this particular case that even the number of moles of sodium oxalate from the acid are the same as 0.03 in terms of the molarity. So there we are. So meaning that we have known 0.03 is the number of moles of what? Of oxalic acid at the same time sodium oxide produced by that particular oxalic acid. But remember, we have the other original oxalic acid, sodium oxide. So it and this, all of them were reacted together with the potassium manganate, what? 7. So now we go for that particular case. Potassium manganate 7, I'm just going to write the equation without wasting a lot of time on that, because it's not really necessary to write the half equations since we already have information about the half equations. So I'm just going to move and we just see what actually comes out. So you have the equation. Let me use another color here of 2 potassium manganate 7, this one. Even if I keep quiet here, you can see what I'm doing. This is a solution. Reacts with the 16 hydrogen ions and of course 5 oxalate ions. Oxalate is written just like this with that, and it is in solution. This gives us 5 carbon dioxides. No, it's going to be giving us 10 carbon dioxide moles it gives us 8 water molecules. This is the liquid, and it gives us also 2 manganese 2 ions molecules, Mn2 moles of manganese 2 ions. So we have this kind of an equation. We know very well where it is got, that the permanganate will always decompose to give us water and manganese 2. That is the half equation. Then oxalate ions will always give us what? They always give us carbon dioxide. Remember, the permanganate requires 5 electrons, and when you look at what? At the oxalic acid, it will produce 2 electrons. Okay, so now I go for the calculation as quick as I can. I've been given 0.02 molar potassium manganate 7, and the volume required in that particular case was, if I'm not mistaken, I think it's 33.4. At 3.4. So I will get the moles of the permanganate. Let's say the permanganate moles. Permanganate moles equal, we quickly do it because that's how I'm just doing it like that. You get the 0.02 times 33.4, and you divide the whole of this one by 1000. So I'll have got the moles of the permanganate. So this is going to be giving us 6.68, I think so, times 10 to the power, let me see, I don't want to make any, even a slightest mistake, the power 4 moles. So we've got the number of moles of the permanganate. So in this particular case, we're going to find out the number of moles of the oxalates, since we've already known that 2 moles react with 5 moles. So, looking at the fact that 2 moles of the permanganate, you can just write Mn cos O, O4 minus, is reacting with 5 moles of the oxalates. You just write it just like that in ionic form to save time, like that. Then I can move on and I say therefore we shall say that if that is the case, therefore moles of total, remember that this is all the oxalate ions available in solution, equal to now 5 out of 2, then we multiply it by the 6.68 times 10 to the power negative what? 4. And this is going to be giving us a good value. Now let me see. I'll try to manipulate quickly and I'll be able to get that answer. This one is going to give us what does it give us? It gives us 1.67, if I'm not mistaken, times 10, but I think I'm not mistaken, to the power negative now, instead 3 moles. But remember, these moles are in a volume that we actually pipetted. So it means that 25 centimeters cubed of the solution that we are using has 1.67 times 10 to the power negative 3 moles of the oxalate ions. But total, all the oxalate ions are variable. If that is the case, how about if I'm having 1,000 centimeters cubed? Because I want to get everything in 1,000, that the other ones that we got are not wasted. Of the same solution, we'll have 1.67 times 10 to the power negative 3 out of 25. Then we multiply this one by 1000. If you check properly, this is going to give us some good number. So this one is going to give us around 0.0668 molar. So we have this as the concentration of all the oxalic ions. But remember, the oxalic ions that we are having in oxalic acid were 0.03. So we shall get now the other concentration of the oxalic ions originally present in the mixture by subtracting the total minus the ones of the oxalic acid. So we're going to say that molarity or moles, we just say moles of original oxalate ions equal total. Now when I talk of total, you know that I'm meaning this 0.0668 minus moles from the oxalic what? Oxalic acid. This is going to be giving us 0.0668 minus, remember the other one was 0.03. So this is going to be giving us the answer as 0.0368 what? 8 moles. They are still in concentration form. There we are. So the answer in that particular case is 0.0368. So we move on. Now we're supposed to find, now that we've got the molarity of the sodium oxalate that we are interested in, the one which was originally in the mixture, the pure one, we can now get its mass in grams per liter. How? You get the molar mass, in this case you say the relative formula mass of sodium oxalate. You show the working and say equals to 2, just say 2. We know well that sodium is 23, 2 times 23, then plus 12 times 2, and then we have 16, which is oxygen, times the 4. You get the answer, because it is anhydrous. Of course, this one you don't need to even look at, it's anhydrous nature. It's already clear. It gives us 134. If that is the case, it means that mass of this same sodium oxalate will be given as, sorry for that, will be given as of sodium or oxalic sodium. Let's continue using the sodium oxalate. It's just like this. Is given as the relative formula mass times the number of moles. So we're going to be having the 0.0368 then you multiply it by the mass, which is 134, and you can easily get your answer as 4.9. 4.9312 grams per liter. So you have 4.9312 grams per liter. So now we want to find out the percentage composition. We shall say that percentage of oxalates equals to the mass of the oxalate out of the total mass of the mixture, and the whole of it is going to be multiplied by 100 because we are getting percentage. So this is going to be giving us 4.9312. Of course, you can maintain the decimal places as 2, so as 1, 8.7, then you multiply this one by 1000, and you'll be able to get your final answer as 56.68%. If there is any error, you can always correct it freely. So that's how we deal with such a question. It looks lengthy, but there is no big deal. You can always do it. That's one of the easiest questions, but once you master these, then you'll be very fine. So don't forget to subscribe to my YouTube channel, and you keep watching. I keep on posting new videos about chemistry majorly and many other issues, so you keep on checking, liking and commenting, and everything is going to work out. So I'm leaving you with my contact, my YouTube channel. Just search for Tumwine Joshua, and you'll be able to see a face that looks like mine. Just click there and you see so many videos in the YouTube. Anyway, there are not so many, but there will be many in as soon as time allows. You can send a question to my email, joshmwine@gmail.com, and maybe WhatsApp. This is 0705 52 70 and 38. Thank you very much, and I wish you the best.